Okay, as we saw in the book, the field for an electric dipole is basically this equation. The book makes a claim that I had a little trouble believing, and they said that when you double your distance from the center of the dipole, it makes your field drop by a factor of 8. And I started thinking about, is that always true? And turns out that it is mostly true. It's just an approximation, though. So the book says it's an approximation. I just wanted to just show you something real quick. So it turns out that what I've set up here is basically the field equation right here. And the K, the Q, and all that's stored up here in these constants. I'll send you this also so you can tinker around with it. But basically, P is the distance that you wish to be away from the center of the dipole, and NP is basically some multiple of that distance. So the book claims that if you double the distance, so if I make N2, then the top here divided by the bottom would give me a factor of 8. So here's what's going on. Imagine that you had a field set up by an electric dipole. It looks something like this. Don't worry about the middle, but looking at these arches. So if you go over to t equals 2, if you go over here to 200, it means you're 200 somethings away from the center of the dipole. If you go over to here, let's say that's 400. If you go over here, that's 600. You'll notice that the y-coordinate represents how strong the field is. So when you go, let's say from 200 to, let's say 400 to like 600 to like 800, you can see the field value is decreasing as you go. The other side is the same game. It's just that you're going in the direction opposite, so your field is negative. So that's the idea. Now, turns out that there's a little dead space in between here, and that's where this particular part, this little denominator here, 1 minus, see this right here, 1 minus d over 2z squared. There are certain values of z that make this particular portion a little more interesting. So that's this part in the middle, and it might look vertical to you, but it's actually not quite straight up and down. It's a slight bit of non-straight up and downness in there, but boy, you gotta really zoom in, and it's because k is such a large number. Don't worry about it, okay? Just as long as you understand that my field equation is being represented like so. All right, so this axis then is d for distance, which I'm calling a few things. I'm calling it z, I'm also calling it p. Okay, and I'm sorry, I said that wrong. It's z or p axis. D is one of the values on here. It's the length of the dipole, actually. And basically, you can imagine the dipole's just chilling right here, and you're just basically walking away from it in this direction. So if you go all the way out to here, you'll find the field strength is whatever, 300 and something. Okay, so the ratio then, if you double your distance, that's NP is 2P here, is not quite 8. It's 8.00002, okay? Also, if you make this a 3, you do not get a factor of 27. You get 27.00008. If you make this a 5, you do not get 125. You get 125.0004. Actually, the approximation gets worse when you make bigger jumps onto the x-axis further out. Okay, also what affects it is your p itself. So right now I'm at 380, and I'm comparing 380 to 760. Let's put this back to a 2. So since this is a 380, doubling it would give you 760. So this is measuring the field at 760 versus 380, and you can see the accuracy here is not quite 8.0. When you change this to, let's say, 200, now you're comparing 200 to 400, and it's actually a different ratio. And that all makes sense because of the placement of the letters, but also we can see that there's varying amounts of accuracy to the statement in the book, depending on where you stand, and also depending on the values of D versus Z. So not something to really worry about, but you can play around with this thing. And please understand that this field equation is only correct when you are in this very specific situation as shown right here. So the dipole has to be oriented, let's say like this, see? And then this mark is z equals 0. And then this is one of your charges here. Maybe it's the positive or the negative. And then you are marching, you have to march along this line. So you have to go stand up here, see? And you say, oh, I feel both charges. So maybe this is the positive and this is the negative. You say, I feel the presence of two charges. All right? This gap here is called D for dipole. And the field that you feel is given by the equation. The magnitude of the field that you feel is given by this equation. Magnitude of E is 2kq over z cubed times, and then we have a d over parentheses 1 minus d over 2z squared squared. What a mess, right? What a mess. Now, you might think, well, that's super messy, right? And it is, but it gets worse if you leave this green line. So if you move off this green line, then it spoils this completely. So that's very unfortunate. But it'll also be such that this no longer looks this way, right? Now the textbook claims that when you double the distance, this would be exactly 8.0, which it is not. And when you triple the distance, putting n equals 3, you would get 27.0. And when you make this n equals 4, it's 64 down here. And when you make this a 10, it's 1,000, which it seems pretty accurate for the most part, right? Okay, so if we do go with that assumption, what it allows the book to do is to take this statement and say, look, as z gets really big, this fraction here that's being squared, and ultimately it's fourth power really, that guy is going to vanish. So they're basically allowing us, even though it's not perfect, they're allowing us to state that the magnitude is just 2kq d over z cubed times a 1 on the bottom, because if this green part goes away, then it will literally collapse down to just a 1 squared, which is 1. Okay? All right. So it turns out that this is used, and the difference between this and what's above it is that tiny little error that we see here. See? The little error after the decimal point. So we do seem to find the book trustworthy again, even though mathematically this limit is not really done properly. If you really do LIM z goes to infinity of this, you actually get 0. You do not get this expression. And that is why, you know, sometimes the calculus folks wonder about the notations in physics. We're not really doing a z goes to infinity limit. We're doing a d is much bigger than 2z. So we do this double greater than symbol to mean if d is excessively bigger than 2z, no, I did that backwards. If 2z is excessively larger than d, then this becomes an approximation. And you can see that it is quite accurate. Okay? There you go.